Okay, so this is the example of unit D0, page 11. This is actually a continuous example from the previous example problem. We kind of stopped in the middle. Use of the Reynolds transport theorem. In the previous example problem, I emphasized Reynolds transport theorem being a building bridge between Lagrangian and Eulerian methods. So let's just illustrate how it is done. Okay, so let's consider again the flow from the fire extinguisher. It's the exact same picture here. Okay. Now once again, let extensive property of interest be the system mass, B equal to M. Okay, and write the appropriate form of the Reynolds transport theorem for this flow. Let's take a look at it. So I'm going to use the exact same figure we used in the previous example problem. So I'm going to do Reynolds transport theorem developed here in this particular problem. Okay. Once again, extensive property of the system is mass. If so, lowercase b is b over mass. So in this case, mass divided by mass, which is 1. Okay. So Reynolds transport theorem is remember dm6 dt, this is reference side, which is equal to dmcb dt plus m over dot out minus m over dot in. This is basically flux of the mass across the control surface. You can express that using integral over the control surface rho times v dot n dA. Okay. This is the mass flow rate. All right. So this is a Reynolds transport theorem. That's it. It's a fairly simple deal. And then if I stop here, then you react like, so what? So what? This is Reynolds transport theorem. Good. Does it solve the problem? No, not really. Reynolds transport theorem doesn't solve anything. It is a building bridge between those two. Okay? So let me just write Reynolds transport theorem here. Okay? Reynolds transport theorem says dm6 dt is equal to dmcb dt plus m dot out minus m dot in. So this is the Reynolds transport theorem acting like building bridge between, connector bridge between Lagrangian to Eulerian. Okay, good. So let's do so. So let's say this is the equation 1, principle of conservation mass. This is equation 2, Reynolds transport theorem. Can we combine those? Yes. We can combine those. If we combine 1 and 2, what do you have? If we combine 1 and 2, oh, wait a minute. Equation 1 says dm6 dt, left hand side is 0, right? Oh, okay. So we come up with a governing equation called continuity equation, which is 0 to dmCB dt plus m dot out minus m dot in. Okay. So I got this equation by combining Reynolds transport and conservation mass principle. This is called governing equation continuity. Does that solve this problem? Somehow, yeah. So how do we apply this equation to this case? Let's do that. So this is the case that flow only goes out across this outflow control surface. So in this particular case, okay, this is 0, isn't it? If so, what is dmCB dt? dmCB dt is equal to, negative of m dot out, okay, I got it. So this is really true by saying this must be some kind of negative value. Yeah, that's right. This is a negative value I found. What is the mass flow rate? Mass flow rate is density of the fluid, cross-section area of the control surface, and velocity of the flow out. This is something very, very meaningful because your next question is, okay, I want to know what is the cross-section area here. What is cross-section area here? If that information is given, that's really great. And the next thing is, what is the density? Actually, out here. This is not out. What is the density of outflowing fire extinguisher fluid? Oh, by the way, what is the average velocity across this cross-section, B out? Okay. If those informations are given, oftentimes given, okay, you can determine how much does it take to empty out this tank, right? Okay. Because you determine the mass flow rate across this control surface. Negative of that is going to be the time rate of change of mass within the control body. So this statement is true. And also, you can actually determine the value. Rather than saying some kind of negative value, you can say, well, it's going to be 20 kilograms per second. So if you have 100 kilogram mass within, it's going to take 5 seconds to empty out the mass within the tank. So you can use this equation to solve the problem. Without Reynolds transport theorem, either you get stuck here or you get stuck here. Okay? No one is solving the problem. Too bad. I don't have to teach this fluid mechanics if there's no Reynolds transport theorem. But flip side of it is everybody funked this class because no one can solve anything. This is how significant Reynolds transport theorem really is. This is a connector bridge between Lagrangian to Eulerian. Okay? So I hope you pick up the basic concept. Basic concept of Reynolds transport theorem is behind everything in Unit D, control volume analysis, which is essentially not in a shell of this fluid mechanics class. That's it.